Hello everyone, welcome to my talk. I'm Donghyun Yu from Unist. Jiun Min is equal contributor of this work and my advisor is Yuseok John. Also, this is joint work with Yonsei University. Today I'm gonna talk about our work, Efficient ROS Address Sanitizer. ROS is a programming language that guarantees memory safety by leveraging strict safety rules which are ownership, borrow checking, lifetime inference, and bound checking. Thanks to these memory safety features, ROS has gained popularity in major operating systems such as Linux, Android, and Windows. Unfortunately, these safety rules are too strict to make implementing certain features challenging, such as double linked lists. To address such implementation challenging, ROS additionally provides unsafe ROS where strict safety rules are not applied. You can use such unsafe ROS by adding unsafe keywords in source code, and within unsafe source code, you can perform low-level operations that omit ROS strict places. However, as strict safety rules are not applied to unsafe ROS, memory bugs can occur in the unsafe ROS. As shown in the graph, ROS security database reported 581 memory bugs in the ROS program over the past 7 years. It means that, similar to C and C++, there is non-memory safety guaranteed area in ROS programming language caused by unsafe ROS, and there are still security holes that ROS compiler cannot guarantee. So, to continuously use ROS in memory-safe manner, we should detect and eliminate these memory bugs stemming from unsafe ROS. To detect these memory bugs caused by unsafe ROS, we can use Address Sanitizer, which is one of the most popular techniques. And the ROS compiler already supports compiling ROS programs with Address Sanitizer and other sanitizers with compiler flags. Here is how Address Sanitizer works. Address Sanitizer inserts red zone before and after the objects to provide memory safety by maintaining a shadow memory that represent the validity of the process virtual address space, and a shadow memory byte can be encoded to represent red zones. And instruments for all memory access sites to track memory access validity. However, the existing address sanitizer was designed without consideration for the nature of lost memory errors. Even most of source codes are protected by ROS safety rules, Address Sanitizer instruments all source code without consideration of ROS safety policies. So its runtime overhead are known to be substantial, mainly due to memory access tracking on lost programs. So here is a question. Should we apply the Address Sanitizer to our ROS source code? The answer is no, because most of memory accesses are already checked by ROS security rules. More specifically, let's assume that we just adapt Address Sanitizer to the ROS program as it is. Considering the safety rules, we can divide memory access site into safe and unsafe code area. If we apply Address Sanitizer to ROS program as it is, it instruments all memory access sites without consideration of the ROS safety rules. It indicates that memory safe codes are inspected twice by ROS compiler and Address Sanitizer. This is because Address Sanitizer cannot identify which memory accesses are protected by ROS safety rules. Since many memory accesses are already protected by internal checks, ERASAN performs redundant and unnecessary memory access checks. It leaves us an opportunity to reduce such unnecessary checks by instrumenting only memory unsafe codes which are not governed by ROS safety rules. So, to get an idea of how to eliminate this redundant check overhead, we firstly investigated our memory bugs over the past 7 years. Among the all 581 reported bugs over the past 7 years, we analyzed 131 memory bugs which are consisted of buffer overflow, rejector free, and double free bugs. Consequently, we found that all memory bugs are related to incorrect memory access through a low pointer. In here, a low pointer is a pointer that can point to any memory sites without consideration of ROS safety rules. Also, pointers alias to a low pointer can cause memory bugs when it comes to temporal memory bugs. The reason why alias pointers with low pointers can trigger temporal safety bugs will be discussed later. Through this analysis, we identify the two root causes of lost memory bugs. First, temporal and spatial memory safety violation bugs can be triggered by low pointer. Second, pointers alias to low pointer can trigger temporal memory safety violation bugs. Consequently, instead of checking all memory accesses, we can significantly reduce performance overhead by only checking memory accesses through low pointers and their alias pointers. We also found out that low pointers and their alias pointers have a much smaller portion of raw source code compared to unsafe raw source code, which indicates that focusing on a low pointer will have a lower overhead than on unsafe ROS-based dynamic detecting approach. Based on these two key findings, we propose an ERASAN, an efficient address sanitizer which fully utilizes security rules and memory bug patterns of lost. Let me give you an overview of how ERASAN works in three modules. First of all, we need to find a low pointer which can be a root cause of memory safety bugs in ROS programs. To preserve the low pointer information, ERASAN annotates low pointer in MIL level. MIR is a unique ROS IL level that has low pointer information that cannot be gathered from other phases. And it identifies unsafe memory access sites by using points to analysis in LLVM-IL level. In this module, it not only finds all unsafe memory access sites, but also conducts further optimizations to trim unsafe memory access sites that are actually safe. Lastly, ERASAN selectively instruments only those unsafe memory access sites to significantly reduce ASAN's runtime overhead on ROS programs without sacrificing its detection capabilities. By doing so, ERASAN can leverage ROS compiler-based security rules and ASAN's detecting capabilities with very low overhead. Let's take a look at each module step by step. Low pointer information is only available at the MIL level, as a low pointer is transformed into a pointer with the same time of the safe references in LLVM-IL level. It makes hard to differentiate a low pointer with other safe pointers which are governed by lost safety rules in LLVM-IL phase. Because raw pointer is a unique information for lost, or the pointers should have the same type in LLVM-IL level as other program languages like C and C++ also use LLVM-IR. To handle this problem, we find all low pointers in MIL level by modifying ROS compiler code and annotate metadata information to corresponding LLVM-IR instructions which can be visible in LLVM-IR phase. It enables us to preserve the low pointer information in LLVM-IR for later static analysis. Next, after we annotate all low pointer information, we find all pointers which have alias relationship with low pointers. To do so, we firstly identify the allocation sites that can be pointed by the low pointers by using points to analysis. Starting from the low pointer operation, we conduct a backward points to analysis to find all possible memory allocation sites that can be pointed by low pointers in a conservative manner. From the identified allocation sites, we track all memory access sites and mark them as unsafe memory access sites which might have an alias relationship with low pointers. This process enables us to find all memory access sites that can trigger memory bugs. From the previous analysis, we have found all unsafe memory access sites. However, as we have conservatively found memory access sites, there is still an opportunity to reduce redundant checks. To further precisely find unsafe memory access sites, we need to consider the types of memory bugs. There are two types of memory bugs: spatial and temporal memory bugs. In terms of spatial memory bugs, ROS typically prevents buffer flow through bound checking on safe pointers such as references. Therefore, unsafe memory access sites are checked by these ROS internal bound checking do not require additional ASAN checks. However, low pointers are capable of bypassing these bound checks, allowing them to access invalid memory. Therefore, only low pointers can cause spatial memory violation bugs. Considering this, ERASAN doesn't have to consider the other pointers, but only low pointers. So ERASAN only checks the memory access through these low pointers to detect spatial memory bugs. However, in the case of temporal memory bugs, ERASAN needs to check not only low pointers but also alias pointers with low pointers. And here is an example. ROS prevents use after free and double free through its life safety rules. However, when a safe pointer and a low pointer are in an alias relationship, they may still be vulnerable to temporal memory violations. This is because low pointers and their alias pointers are not applied to ROS lifetime safety rules. So we need to identify all pointer accesses related to low pointers. Nevertheless, temporal memory violations are incurred only after a memory is freed. This enables us to get rid of check instrumentation to unsafe memory access before the memory gets freed. And as the allocations of memory differ from its memory type, we conduct different optimizations according to memory types. In the case of heap object, ROS compiler automatically inserts drop function to the heap objects, and the temporal memory bugs occur only after the drop function. It means that we don't have to keep check instrumentation before the drop functions if they are alias pointer memory access sites. Therefore, ERASAN only instruments memory access sites after drop function, and it enables us to optimize redundant checks among unsafe memory access sites. In the case of stack, the temporal memory bugs can only occur after the stack is cleaned up, like the heap object did. It means that after the stack object has been cleaned up, it can be exposed to stack use after scope. Therefore, ERASAN keeps check instrumentation to these memory access sites. Lastly, we have found unsafe memory access sites from the previous analysis. With the previous analysis information, ERASAN can determine which memory access sites need to be inspected by ASAN. Then it selectively instruments only those unsafe memory access sites that enable low overhead during runtime while maintaining detection capabilities. And next is the evaluation part. We evaluated 5 aspects to evaluate the effectiveness of our work. To precisely and fairly evaluate each proposed technique of ERASAN, we prepared 4 different baseline configurations. The first one is the modified version of the ASAN. The second one is the ERASAN unsafe mode, which conducts unsafe block-based approach. The third one is ERASAN low PTR mode, which tracks all memory accesses that have alias relationship with the low pointers. The last one is ERASAN thread mode, which turns off optimization within multi-thread functions. To evaluate how efficiently ERASAN removes the ASAN checks, we measure the number of removed checks in static time against 23 benchmark tests. As a result, ERASAN removes about 90% of sanitizer checks. The reason why ERASAN achieves a higher reduction rate is that it can remove our instrumentation to save memory access, unrelated to low pointer and its alias pointer. Then we evaluate runtime overhead to check whether ERASAN reduces its runtime overhead by leveraging ROS unique memory management. Since ERASAN only focuses on memory accesses by load pointer and its ls pointers, it improved performance by about 240% compared to original ASAN. The result shows that our approach is more efficient than the unsafe block-based approach, and each drop access optimization for object type can increase the runtime performance. Our result also shows that ERASAN can detect all 28 reproducible CVEs as same as ASAN. This shows that ERASAN has full detection capability. Lastly, we check reduction rates to evaluate how efficiently ERASAN removes the memory checks compared to the state of the art, which is known as ASAN --. As shown in the result, ERASAN can remove 56.88% of checks that even ASAN --, cannot remove, because it identifies the redundant checks more precisely regarding the ROS environment. And this is conclusion. ERASAN efficiently reduces performance overhead, achieving 90% unnecessary check reduction and about 240% performance improvement while keeping the same bug detection capabilities. And that's it. Thank you for listening to my presentation, and if you are interested in more details about our research, please refer to our paper and open source. Thank you.